All right, well, it is 10:30. I am going to get started. Um, so what we'll do today is to set up everything and also to give you, everything that you need for another programming assignment. So that means that we're going to have two programming assignments going on concurrently. So that means, well, it's a good thing and a bad thing. It means you can kind of choose to choose which one to work on. It's kind of another good thing is when you write code for one, you might realize, oh, okay, so that's what I was missing in the other one. But basically, we will end up with two concurrent programming assignments going on at the same time, and then on Wednesday there'll be three going on at the same time. So that it's once you understand the basic idea of how to write code in TTP ASM to implement the C code, it really doesn't matter what code I gave you in C because the translation process is pretty much the same. Um, so anyway, um, I will present the programs that you need to work on today, or that you need to understand in order to get your homework done. So the first one I'm going to present is going to have a function call that returns the value of two other function calls. So we'll go ahead and take a look at add.c. This is a program that I'm just implementing today. So as usual, the left-hand side is the C code, the right-hand side is the assembly code. So in the C code, I have the really kind of typical pound include stdint.h, which is standard integer.h, because without this header file, uint8 underscore t is not anything that is defined. So that's why we have to do the pound include of this file. So now we have uint8 underscore t add, and it has two parameters. Okay, so I think we might have looked at this program before, but the way that I'm using it today is a little bit different. So I'm gonna say this is just returning x plus y. Okay, so pretty easy thing here. And then we have int main, and inside main we have a local variable. Okay, we'll call that let's try not to use x and y. I'm gonna call this one v. So v is a local variable in main, and v is gonna store add. That would not work, would it? Okay, so we'll say v equals to 2 first, and then we're gonna do v gets add v. Oh, let's just go all out like that. Okay, return 0. Okay, there we go. All right, so now the question is, what do you think the value of v should be after line 12? In other words, do we know how to look at line 12 and serialize what it is actually going to do, and just kind of manually look at the code and figure out what is the return value of the final add, because it has 3 adds, right? And then we want to say okay, what is the resulting value in v after the whole thing is done?
16.
16. It's going to be 16. That is correct. Okay, so 2 plus 2 is a 4, 2 plus 2 is a 4, 4 plus 4 is an 8. So it is 8, not 16. Okay, so we think it is 8 and not 16. So one way we can confirm that observation is really just to compile the C code and run it. So let's go ahead and do that. Okay, let me get out of this debugger, clear the screen. gcc-g-o add.c, and gdb add, and we want to put a breakpoint on line 13, run the code, and then we say, okay, what is v? It is indeed 8. Okay, all right, so we kind of know what the C code is doing. Now we have to implement it in the assembly code. So when we go to the assembly code, the few things that we have to remind ourselves is, how do we push arguments on the stack? What are the responsibilities of the caller as opposed to the callee? How do we return a value? What do we do with the arguments after the call has returned? And so on. Okay, so all of those are caller callee agreements. Okay, because add in this case has no local variables. Main, on the other hand, has a local variable. So now we have to remember, okay, with a local variable in a function, how do we allocate the space for the local variable, and how do we access it? Okay, so now we're going to switch over to the assembly side. Okay, so from here on, I think the entry code is going to be pretty standardized. Okay, it's a no op, and then we call main. Main has no parameters. You can see there are no parameters here, so there are no arguments to push. So we are just going to say, okay, let's specify the return address, LDI A.6+. Okay, so this was explained in the previous class. The dot is representing the address of the opcode of the LDI instruction on the same line. And 6 means we are specifying the return address is 6 bytes from the address of the LDI opcode. Decrement D, STDA, and then JMPI to main. And when we come back, we want to get to the halt instruction. So this is the entry code, which is treating main as any just normal subroutine. And now we can specify add as a function. So add is fairly easy. Okay, I think we have talked about something similar to this already. So we just say, okay, add. From the perspective of add, the frame is going to look like this. Okay, we're going to have add underscore x, having a label. Okay, first of all, we say, what about LVS? Okay, in other words, what is the number of bytes that we need to reserve for local variables? You guys look at, add and go like, but it has no local variables. Fine, okay, then it has 0 bytes needed for local variables. Then x, which is the first parameter, is going to be add LVS 1+. The 1+ here is referring to the size of the return address, because even though there are no local variables, we still have a return address that was pushed after the first argument. So that means the return address is at the base of the frame. Okay, so we'll do this, add y, add x 1+. So this time this 1 is referring to the size of x, because x takes up 1 byte. So this gives us the 3 labels that we need in order to handle things on the stack. So from a pictorial perspective, okay, this is not going to be the best way to describe it. Okay, so from the pictorial perspective, this is me drawing a stack here. The first, the highest item, the item at the highest address is y. The second highest item is x, because it's pushed after that. And then the last item in this particular frame is the return address. So now we have these 3 items on the stack. And together, these 3 items forms the frame of the entire thing. So this means this is the base of the call frame, or simply called frame. I'm fairly sure that we talked about the concept of a frame. Have we talked about the concept of a frame? So a frame, includes your local variables, if any, the return address, which is the only thing that is not optional. It is mandatory to have a return address, and then also parameters, which are also optional. So that's basically what the frame looks like. And this is also why, when we look at the actual value of add x as a label, it is basically 1, because it is 1 byte from the base of the entire frame. Now, if you ask me, but where is the frame? The answer is, well, we don't exactly know where the frame is. It kind of depends on when we call add, where the stack pointer is pointing to. But then again, I should not need to know exactly where the frame is, okay, because it's all relative to where the stack pointer points to. Yes?
Is it okay to call a frame just a block of code, for example? the
Not
function
code.
Itself? Huh?
Not a block of code. It is a block on the stack that provides the context, the data context for the function to operate. But it is, it consists of all the things that the function needs in order to do its own thing for local variables, and also the parameters, and also the return address. So by the time the function is done, it goes like, okay, I know how to get back to the caller. All right. So from this perspective, when we want to add, x and y and then return that as a result, we can do something like this, load A with add x. So now A is the offset from the base of a frame to parameter x, but it is not an address because we still need to add the stack pointer to it. The stack pointer at this point is also pointing to the same address, which is pointing to the base of the entire frame. So by adding the stack pointer to the offset of x, we now get the address of x. But we need the value of x, not the address of x. So LDAA will give us the value of x. So now we can do the same thing with y. Okay. Now this is not. Oh, okay. I take it back. This is add. So add BD. This is now the address of y, and then LDBB. This is the value of y. So at this point, I have parameter x sitting in register A. I have parameter y sitting in register B. So the only thing I need to do is to perform the add operation. And register A is the register to use to return a scalar type. And an unsigned 8-bit integer is definitely a scalar type. So that means, okay, at line 26, we have now specified the return address. So now it's time for us to return. And I forgot one more thing, okay, which is kind of not needed in this case, but it is usually needed regardless. So I need to reserve space for the local variables. So that usually is just subtracting this much from the stack pointer and then adding the same to the stack pointer. So when we exit, we have to do LDIB with add LVS, and then add that much to the stack pointer to deallocate the local variables. And then after that, the stack pointer will be pointing to the return address again. At this point, it should. So now we have LDBD, increment D, because we are popping the return address from the stack, JMPB to continue execution at the caller. So this code here is, if I want to describe it, it is as boilerplate as it can possibly get. Okay, the way we get to the parameters, the way we allocate local variables, is as boilerplate as it can possibly get. Okay, it should be somewhat boring at this point of this class. Okay, so now we can move on to main. Okay, so main is a little bit different. So once again, I want to draw what does the frame look like from main's perspective. So main does not have any parameters. So the first thing that the caller is going to push is the return address itself. But then main also has a local variable v. So v is at the lower address compared to the return address, because v is allocated after the return address was pushed by the caller, and that's why v has a location that is lower than where the return address is pushed. So this is the base of the frame. Now if you ask me where is the stack pointer pointing to, that's a kind of complicated question to ask, because at the entry point where the label main is, the stack pointer is actually pointing to the return address, because the caller has no idea how much space I need to allocate for the local variables. So that means the function itself, in this case main, is responsible to allocate and deallocate for its own local variables. So I think that point is kind of important to make. So now we can work on the offsets. Okay, main v is the only local variable, so it has an offset of 0. And then main LVS, which is the local variable size, is main v, which is the last, but it is also the only local variable, 1 plus. This one is referring to the size of local variable v, but because it's an 8-bit unsigned integer, it only takes up 1 byte on the stack in the frame. So now we can now say, okay, but that's about all we need to do, because there are no parameters. So these are the only 2 labels that I need to define here. Now this time LVS is non-zero, which means the allocation and the deallocation of local variables is not optional anymore, because we do have 1 byte to allocate. Most people would just say, well, we could have allocated with a decrement D. That is true, okay? Absolutely no problem in this case. But when you use decrement D, it means you can only do the allocation for exactly 1 byte here. If I later on choose to have more local variables, then the decrement D will need to be changed. So that means, at the expense of some code, some additional code, I would much rather use a much more boilerplate approach, which is LDIB with main LVS, and then subtract that much from the stack pointer to allocate for all my local variables, which is 1, okay, in this case. But then I would, for me, this is how I would do it. LDIB main LVS, add DB, because, I like to do things in a structured way. So that means if I allocate, I automatically do the reallocation, and might as well throw in the actual return code here. The return code is boilerplate, okay? In other words, this is the typical way that I return, okay? If I'm going mindless, okay, and I want to minimize the amount of thinking, this is how I would do things, okay? So now, the question is, where is the stack pointer? Okay, so let's go ahead and take this code here. At this point of the program, the stack pointer is actually pointing here, because we have not gone through the actual code to do the allocation, but later on, after this subtract, then the stack pointer is going to be decremented by 1, because LVS is 1 in this case, so now the stack pointer points here. So that means the base of the frame is always at the same location, but the question is the stack pointer pointing to the base of the frame? The answer to that question is, how do we get the stack pointer to point to the base of the frame? Is we have to use instructions, line 46 and line 47 in this case, in order to move the stack pointer to where the base of the frame is supposed to be. So by the same token, okay, if you say, okay, so if I am looking at the stack, after the add DB, then the stack pointer is pointing back to the return address. And that's why, the next instruction, LDBD, will retrieve the return address so that we can go back to the caller. So this is kind of my way of documenting what the stack would look like at various points of the execution of this code. Hopefully, this is going to help people understand how the stack is being used and how we adjust the stack pointer in order to make it work. Do we have any questions at this point? No questions? Okay, so if there are no questions at this point, then we are going to kind of put in the actual function code. The first one, okay, before we do that, we have to assign a value of 2 to v. Okay, so the way that it's done is this is the offset, this is the address, and then this is the right hand side value, which is 2, and then this is how we store 2 to local variable v. So once again, I am not commenting the code so that you can do it, okay? Because that is I think it's a valuable exercise to document the code after the class, so that when you revisit this code, you go like, okay, what is this line doing? What is in a register after this line executes? So you should be able to identify what register has what after each line of the code. And I'm not really just saying, oh, okay, on line 52, register B ends up with the value of B. But what is the value of main underscore B? How does that relate to the C code? Okay, so always make sure that your comment relates to the C code, because that is the connection that you need to make for the final exam. All right, I'm just checking my recording. Everything is still good. Just want to make sure. Okay. So now we look at line 12, okay? So what do we do with line 12? Well, there are 3 calls to add. The question is, which one are we going to handle first? I think most people can agree that I cannot perform this particular add, because in order to perform this particular add, I need to have the 2 additional adds already done. So that means, out of these 2, I could have done this one first, but because of the way we push arguments on the stack, it makes more sense to get this one done first. Does that make sense? In other words, if I'm when I'm serializing, okay, which means you're turning things that does not seem to have a ordering into something that is linear, which means do one thing at a time and then do everything in a sequential order. So that means, I am looking at the dependency of everything, and also the fact that when we call a function, the arguments need to be pushed where the last one is pushed first. It kind of makes sense to handle this call first. So I'm going to pause a little bit and see if there are any questions about what I just said. Are we okay with that? All right, so let's do that, okay? So this means, I just need to get the value of v, okay, and pass it to add and then just push it on the stack. So I understand that the value of v is already in register A, and I could just use register A in this case, but I'm not going to shortcut anything. So what I'll do is I'm just going to pretend that, I have never seen the value of v before, and I'm just going to have to get it from the frame. So I do a LDIB with main v, add bd, st, ld, because I'm reading, not writing, not overwriting. So ldbb, okay, that should be sufficient. So at this point, after line 59, register B should have the value of local variable v. Yes?
Can you just pass the register A into the function right away?
Say that one more time?
Can you just pass the
Yes.
register A into the function?
Yes, but I specifically said that I didn't want to do that.
Okay.
Because I want to pretend that, let's just say that we don't know, we have never touched v from before, and this is the first time we do it, because I just want to illustrate what, how that's supposed to happen. All right, so now we have the value of v in register B. We have to push it twice, okay, because it is the same, variable. So we have to push it twice, so that means decrement D, st, db, decrement D, stdb, and now we can push the return address, which is LDI, A, B, whatever register you want to use. At this point, no register is quote unquote sacred at this point, so you can use any of the 3 remaining register. The only one you cannot just kind of casually go, I'm gonna modify it, is the stack pointer, which is register D. So decrement D, st, da, db. So now we have everything pushed. We just do a JMPI to add, and when it comes back, I just have to do increment D, because the 2 instances of v, they're still sitting on the stack, and I don't need them anymore because they are really, I'm done with this function call. So at this point, we have register A containing the value of the first call to add. Okay, so I will comment this one. So register A has the right hand add VV. Okay, so I need to call add VV again, but there's something else I need to do first, because after all, this add VV, the right hand side one, is specifying one of the arguments to the last add call. So that means the value of register A here needs to be pushed. So I'm going to push it, okay, which is decrement D, stda. Okay, I will even comment this one, push return value of rightmost add VV. Okay. Are we still doing okay so far at this point? Because there are 2 different caller-callee agreements that are in play here. The first one is the scalar return value is always in register A. The second one is when you push arguments, the last argument has to be pushed first, which is what we're doing here. So there are 2 caller-callee agreements in play, with these 2 lines of code. Are we good so far? Okay. So at this point, I'm going to show you what the stack looks like again, okay? Because we did something with the stack pointer. So what we have here is the stack is going to look like this. We have, add VV, or the value of add VV being pushed on the stack. So that means the base of the frame is not being pointed to by the stack pointer anymore. The stack pointer is now pointing to one location lower than the base of the frame. So if I need to perform the second call, you go like, oh, but we can just reuse V from earlier. We got V in register B, and then we overrode that register B immediately with the return address. So you guys may be thinking, hey, if we just use a different register, then we should be fine, right? No. If I use a different register here, that's fine. Okay, you can use register A, B, or C in that context. But the caller-callee agreement also specifically said the function can clobber or overwrite all of the three registers, A, B, and C. So that means after the function call, which is happening right here, and when it returns, you cannot count on register B still having the same value. Is that okay? So that means, okay, we have to recompute and get the value of register. We have to recompute and get the value of local variable B again. So that doesn't seem too hard, right? Okay, so you go like, okay, we know the template of the code, LDI, B with main underscore V, add BD, and that should be the address. But that is not true anymore, because the stack pointer is pointing to 1 byte below the base of the entire frame. But the label of main underscore V has the assumption that we are calculating the offset from the base of the frame to local variable V here. Now, the base of the frame hasn't moved. What has moved is the stack pointer. The stack pointer is not pointing to the base of the frame anymore. So this add instruction is no longer getting you the result that you want, because after this add here, we will be pointing to the return value of the first call to add instead of local variable V. Okay, so I just want to make sure that you guys can understand what I just said, because this is a very important concept when we have only a stack pointer to play with. We okay with that? This decrement D on line 72, that is the problem. Because the stack pointer is no longer pointing to the base of the frame anymore. It's pointing to 1 byte below the frame, but because main underscore V is defined as an offset from the base of the frame, so that means adding the stack pointer to B or the offset is no longer calculating the correct address to V. It is now calculating the address to 1 byte below where V is located. So the correction to this code is rather simple. We can just do a 1 plus here. In other words, we just say everything is off by 1 byte. Okay, so we'll just add that 1 when we when we try to load the offset, because what we want is ultimately the label is the offset from the frame, from the base of the frame to whatever we need to access. But what we really want is the offset from where the stack pointer points to. So now with this 1 plus, everything is good again, because here we are basically going like, oh, the stack pointer is pointing to 1 byte below where the frame really is. So that means all the offsets that we have calculated should be 1 more than what they are defined. So this will address the problem. The other thing to address this problem is simply to have an increment B over here. This works exactly the same way, but this approach uses 1 more opcode and takes the time of executing 1 more instruction, as opposed to this approach here, which only uses the assemble time in order to figure out the expression, but it doesn't use any actual runtime. So from the efficiency perspective, this one is better, even though both solutions will get us exactly the same thing. All right, so now we can just use the same code again. So now we say LDBB. Now register B does have the value of local variable V, so we have to push it twice on the stack, which is, excuse me, decrement D, stdb, decrement D, stdb, and then LDI 1.6 plus, which is the return address. Decrement D, store that to the stack, which is now our return address. So once we push the return address, we can actually place the call. So JMPI to add. When we come back, before we do anything, we have to increment D twice because the two arguments, meaning this V here and this V here, are still sitting on the stack. So I have to kind of get rid of those two. And now I'm ready to make the third call to add, because what I have done so far, oh wait, I'm not quite ready yet. Okay, so I'm just gonna have to say here, register A has the return value of the middle add VV, okay? In other words, the return value of this add VV is now in register A, but I still need to push it on the stack because it is serving as an argument to the last call to add. So I still have to push it on the stack. So that means I have a decrement D, whoops, and STDA over here. So some of you look at this code and go like, can't we save some time by not incrementing D and then immediately decrementing it? Your observation is correct, okay? We can indeed optimize the code a little bit here. So that means on line 70 and line 72, this is an increment, this is a decrement. They're just really undoing each other, okay? And the same thing over here. On line 93 and line 95, the increment and the decrement are basically just undoing what each other is doing. So why am I supposed to just say, okay, none of you is going to do anything, then we're good. But, okay, a big but here is I don't want to delete lines 70 and line 72 because the increment is because we need to deallocate the argument. The decrement is because we need to push the return value. In other words, they serve different purposes. Now, it just turns out that they cancel out each other, okay? So we can quote unquote optimize the code by getting rid of both of them, but I want the code to be still commented but remaining in the program because they actually are important. In terms of concepts, each one is important, okay? In terms of actually what they do cancel out each other and we can optimize them out. All right, so I'm just gonna pause here and make sure that you guys understand what I just said. I have learned that my interaction with ChatGPT requires a lot of double confirming. It's like, do you understand what I mean? Can you demonstrate an example to show that you understood what I just said? And then ChatGPT would kind of give me an example of something, okay, depending on the topic, to show that, yep, I understood what you just said. So do you guys understand what I just said? More or less. Okay, all right. Well, everything is still being recorded, so in case you want to jot down a little question in your notes and go like, I might need to go back to the recording at about 11 o'clock and revisit that topic, okay? You can write that question down in your own notes as a reminder. All right, so where are we now? We have just pushed the return value of this add and this particular return value of this add here, and now we are ready to push the return address for this add, and then we do the call, okay? So now we switch back to this side and say it is time to push the return address, which is another .6 plus, and then decrement D, STDB, and then JMPI to add again. This is the last call, and increment D to deallocate the return value of the two nested calls to add, and now we have the entire right hand side in register A. So now I'm going to just say register A has the right hand side of the assignment on line 12 of the C code. Okay, so that means register A should be 8 at this point. I just need to store that back into local variable V. So that means I'm going to have to recompute, okay, the address of local variable V. So that will be the label, which is the offset from the frame, and add BD, STBA. So now we have stored the return value of the last add to local variable v. So go like, but don't I need to have a 2 plus over here because there are 2 adds and they're pushed on the stack? The answer is no, because I have deallocated those by these 2 instructions. Lines 102, lines 103 together are deallocating the arguments that are sitting on the stack. So that means that by this time, the stack should be going back to point to the base of the frame. Okay? All right, so I claim that this should get everything done. So now I can run it. I can test run it. So when you test run the code, you need to know what is supposed to happen on the stack. So that means I am expecting local variable v of main to be updated to 8 at this point. So if I were to take snapshots of what the stack should look like, okay, 3yy, copy it over here. That means by the time I get to the store instruction over here, not quite, but over here. So that means by this time, I'm expecting this v to have a value of 8. And in all the prior cases, it is initialized to a 2, but only when I get to this point that v should get a value of 8. So we'll go ahead and check that out and see whether that's what it's going to do. So, and I'm doing this with the main assembler. So if you already are looking at the main assembler, you can actually see the code execute. Assuming that it assembles, assuming that I did not make a mistake somewhere. All right, so it's all done. Go back to the assembler, go to the analysis tab, and I'm expecting an 8 to be stored somewhere. Okay, so let me get rid of that. All right, so getting back to the source code, this is location FF, this is location FE. So I'm expecting asterisk FE equals to 8 somewhere along the trace. I can just go ahead and fast forward a little bit here, and there we have it. The other 2 things that I usually check for is register D, which is the stack pointer, going back to 0, 0 right before the halt instruction. So that's also important because we need to make sure that the stack is balanced and we end up with the halt instruction that is supposed to end the execution of the entire program. So this is a technique that you need to understand for your new programming assignment, which is a recursive call kind of thing. So do we have any questions about this particular sample program, which is not recursive, okay? It is nesting a call of itself inside its arguments, but this does not make it recursive. Recursive means inside the function body itself that it has a call to itself. But when you are calling the function and you have another instance of the call to specify one of the arguments, that is not counted as recursion.
Isn't that called indirect recursion though?
Nope, this is also not indirect recursion. It is not recursion at all.
Yeah.
Because the way it works is this is a call to add, this is a call to add. Based on these 2 return values, you make a 3rd call to add. But the recursion, a recursion means somehow the add function is going to call itself. But there's no code in add, which is the only line that matters is line 5. There's nothing on line 5 that suggests either a direct recursion, which means the function is directly calling itself, or it is calling somebody else that can potentially call add itself, because there's no function call at all on line 5. So it is not recursive. This is not recursive at all. All right, so do we have any questions? Okay, I just want you guys to look at the source code, particularly the C code, and think of what we did in the assembly code, because the assembly code is a little bit long on this side, on the right hand side. So I cannot really show you the entire assembly code on the screen. Are we good at this point? All right, Cool. So now I can show you what kind of code you're going to write for this new homework assignment, which is due 2 weeks from today. So when I specify a due date that is something like 2 weeks from from the assignment date, at the back of my mind, I always worry about one thing: somebody's going to forget that there's homework. So, are you guys going to be okay with that? Having a due date of about 2 weeks? Okay. My kids, go through, when they go through high school, they have projects that has due dates of like in a year. So how do you expect high school students, and I'm talking about like freshman or sophomore, high school students, to be able to track projects that has a due date that is like a year from the day it was assigned? Well, the answer is no, they cannot, but their parents can help. So I don't think it really helps high school students all that much, when it comes to that. All right, so this one is due in 2 weeks. Do we have any questions about the assignment that you were assigned last, I think, Wednesday? So the swap, the swap function, are there any questions about the swap function? The best way to look at the swap function is to go through the C code first, okay? Use the C debugger. You can either go through GDB like what I do in class, or if you prefer, you can use online GDB. But it is important to go through the C code and understand what the C code is doing first before you even get started in the assembly code. Any questions? Okay. I was kind of expecting people would raise their hand and go like, okay, I got a question about the swap function, but there's none, so that's kind of interesting. All right. If that is the case, I'm gonna move on. I mean, is that okay? Alrighty. Okay. But before I do that, okay, I do want to kind of show you what you will be dealing with the new homework assignment. So I'm gonna unzip the file first. It's called Fibonacci. So I'm gonna overwrite all the files, okay, just so that we can take a look at the C code and also the assembly code that is provided to you, so that you kind of get an idea of what you need to do. All right, so on the left-hand side, we have the C code. On the right-hand side, we have the assembly code. Main is already done for you, okay? So there's no need to worry about main. It's already done. It is fib, or F, that you need to implement. So in this case, it doesn't look much more complicated compared to the previous program that we did, but it really is a little bit more complicated, because this one is recursive, okay? If n is less than 2, then it is non-recursive, and we just return the value of n. If n is greater than or equal to 2, then it is recursive, and is doubly recursive, okay? So when we look at the C code, do we know what f is supposed to do? This is also called the Fibonacci number. So if you look up your Fibonacci, Fibonacci, okay, Fibonacci. So the CI is CH because it's Italian, okay? So it's a Fibonacci number, one way to define Fibonacci numbers. And the C code does work, okay? Do we have any questions about the C code? No questions about the C code? Okay, fine. How do you plan to write this code? First of all, are you going to write the entire function f and then hope that it works and then give it some test cases? If I were you, I would not do that, okay? If I were you, I would do something like this, okay? So I'm not gonna save this or send it to you because this is merely a suggestion. I'm gonna put a halt right here, okay? You go like, what? Aren't we supposed to be implementing F? Yes, I'm gonna put a halt here, just so that I can see what the stack looks like at that point, okay? Because I need to know where's the return address and where is the parameter, okay? Can I get to the parameter? Okay, that's kind of what I need to do. So that would be the first thing that I do. The second thing I'm going to do is to look at function f and go like, that looks a little bit complicated. I think I'm just going to write a function that is like this, but a lot simpler, okay? In other words, I would implement something that is a little bit simpler and easier to debug. Something more along the line of, give it a particular constant, I don't care what it is. You go like, but check, 57 is not even a Fibonacci number. I know, it's okay, but I need to check whether the code is working or not. So that means in the code in C, okay, you can make adjustments to that. So that means I'm going to call f of 0 and see if the function is really returning 0, because that's what it's supposed to be returning. I will test it again with 1 over here and make sure that it does return a value of 1, because that's what it's supposed to do. And then I'll try with 2 and see whether it is returning 57 or not, because that's what it is supposed to do. In other words, I would double check and make sure that my control structure for the ternary expression is correct first. Because if that is incorrect, what is the point of implementing the rest of the program? It really makes no sense, okay? So if you can get this particular f, simplified f, to work first, that means, okay, I get most of it working. So now, okay, we do recursion here. But I'm going to simplify the code, okay? So once again, this is not what the homework assignment is, but this is one step in the process to finish the homework assignment, is can I call f at least once recursively, okay? So if I do something like this, then f of 2 would return f of 1, which then returns 1. So you have to, if you do modifications like this, you can also modify the C code and find out what the C code is returning first. Then you make sure that your assembly code is replicating the effect of the C code, okay? So I'm telling you right now that f of 2 should return 1 once I modify f to be the same as line 10. So I would double check that that is the case. Because if the recursive call is infinite, which means it consumes all the stack space, run into the code space, and causing the program to step onto itself, well, let's not worry about the double recursion, okay? Because in that case, a single recursion is already having problems, so we have to kind of address the single recursion first. Is that okay? So if this is working, then, and only then, I would worry about the double recursion. So the double recursion, okay, or having 2 points of recursion in the same expression, is why the sample program of today is important, okay? Because the resemblance is actually, yes, so the resemblance in this case is something has to remember the return value from the first call. I will stash it into register B. You cannot, because when you perform the second recursive call, you cannot assume any register retains its value. So what you need to do is to push the return value from the first call before you place the second call, which also means by the time you do the second call, the stack pointer is pointing, once again, 1 byte below the base of the frame. So the technique that I just demonstrated in today's lecture is going to come in handy when you implement the double recursion. That is where the cursor is located right now. Okay. So that is the whole reason why I gave you the sample program of today, because it's basically going like, oh, so I have to keep track of where the stack pointer is pointing to. And if the stack pointer is not pointing to the base of the frame, I need to remember that and make adjustments accordingly so that I can still access, in this case, my parameter correctly. All right, so that's kind of the key statement, okay? You can always jot down the time and go like, text says something that seems to be important, but I may not be understanding 100% of it right away, so you can go back and revisit what I just said. Okay, so that, I think that is probably something productive And if you want to look at the actual recording time, we are about 49 minutes into the recording. So I'm trying to do you guys a favor so that you know how much to fast forward in the lecture recording to get to the part that go like, oh, okay, maybe that's important. All right. So do we have any questions about this program, or what to do to gradually write this code and debug it? While in doubt, okay, if you say, I'm not even sure I can get to n as a parameter, put a halt instruction right after your code is supposed to have put the value of parameter n into a register. Just stick a halt instruction there, run the code through. If you use a halt instruction, you can actually just run it through Logisim, the GUI, and because you can actually see what is in a register, after the program is at a halt instruction. But it is also more handy or more convenient to use River Spider, because that gives you the entire history of why you got whatever value is in whatever register. So I highly recommend the use of River Spider to kind of write and debug the code, but you can choose however way you want to do it. Some people may feel confident enough to go like, I don't need no simulator. I don't need to simulate the code. I know what I'm programming is going to be right. Okay, I don't have that kind of confidence, but some people may. So you do you and I do I. Are we okay so far? All right. So this program may take a while to develop, okay? As simple as it seems, the concept of recursion it's a very simple concept in a sense, okay? Whether it is recursive or not, the way you call a function does not change. The way you return from a function also does not change. So everything that we have talked about up to this point about the caller-callee agreement, none of that is going like, oh, there's a special case when the call function calls itself, this is the special case. Nope, there is no special case whatsoever in recursion. You just call the same way, you return the same way. All the caller-callee agreement apply exactly the same way in a recursive situation. The tricky part of recursion is if you do not check the condition correctly, let me point to the condition here. If this condition is not implemented correctly, it is possible that you end up with endless recursion, which means the program just doesn't stop. So what do you do when the program does not stop? How do you detect that your program is not stopping? That would be the first question. So that kind of depends on your script, okay? If you are in Linux, okay, because the original code is all implemented in Linux, there is a command in submit that times out. Okay, so let me show you what I mean by that. So there's this command here that times out, and this command basically says, I'm gonna run the simulator, right here, but in 5 seconds, it's gonna time out. In other words, in 5 seconds, I will kill the process. Whatever it has generated into the trace, that's all I'm gonna send to the assembler for analysis, okay? But the problem is timeout is not a universal tool that is available to every single platform. For instance, Mac OS does not implement timeout on the command line. I think Sigwin does not have that either. So that means, if you are using Mac OS, you might need to do some additional work to, kind of do this safe check. So you can look into Mac OS G timeout homebrew, okay, because it doesn't come with Mac OS, and you kind of have to find ways to implement it to make sure that it does work.
You can just kill it with Control-C.
But it's inside the script. If you do a Control-C, you kill the entire script. You're not just killing the simulator, you're killing the entire script. That may not be what you want, because you might want to just kill the simulator so it can still upload the trace all the way to the analyzer, so that way you can still go like, okay, what is repeating? Okay, because usually it will give you a pattern, and once you notice the pattern, go like, okay, either you're not passing n minus 1 and you're just passing n along, okay, or you're using the wrong return address, so it just returns to the wrong spot of the program, and that turns out to be an earlier part of the program, so the whole thing turns into a loop. So G timeout is what you need in Mac OS, and there are ways to compile and install G timeout. This is how you do it. But I cannot include it in the distribution because I don't have a Mac, so I can't even do this part for anyone. So that's one. And then the second one is if you use Windows, you're going to use sigwin. So now you can look up sigwin timeout command. So I think timeout actually does work in sigwin. So you guys are actually, it will work. So if you're using the sigwin option, because you're using Windows, the code does timeout in 5 seconds or so. And you can adjust that timeout period too. I think 5 seconds is already a lot, okay? You can probably reduce it to like 2 seconds, okay, or 3 seconds, just so that it doesn't give you a super long trace that takes forever to analyze. All right. So I'm already kind of giving you a lot of tips of how you can debug this program, but getting RiverSpider to work first is kind of, I would say, a prerequisite. Okay, some people may not believe that. That's what I think. All right. Questions? Okay. How many lines of code do you think you should write before you run RiverSpider or use some other way to double check that your code is doing what it is supposed to?
3 lines.
3 to 5 lines of code, yes. That would be the right order of magnitude, okay? Because some people tend to write, oh, I'm gonna finish the whole program, and then I'll debug it. Nope, write it in small steps, okay? Always write it in small steps and know what those small steps are supposed to do and double check that the program does what it is supposed to, even in very, very small steps. Any other questions? Does anyone know how to use GitHub? Because that's also a good tool to use to kind of keep track of the revisions to your code, just so that in case you make some changes so that the whole program doesn't work anymore, you can just kind of back up. It's like, okay, I can undo this. Okay, what did I have like 2 hours ago when it was partially working? All it takes is for you to remember to check in once in a while. Okay, but it's a really useful tool to help you kind of keep track of the revisions, and you can always check in a version where the code or the comments in that revision says, okay, I got it working up to this part, and the next part will be this part over here. So it serves as a reminder of what else you need to do in the program. All right, so if this is all okay, we are going to move on to talk about structures, because I really hesitate to do that until there are no questions about the current topic. But since there are no questions, there's not much else I can do when there are no questions. So the next topic is about structures and arrays, and for this class I'm not sure whether this is already, yep, it is already updated. Okay, cool. So I'm going to take a look here. All right. I will start with structures. Okay, so structures is the slightly more important topic here. So this is the template of how you would define a structure in C. A structure is similar to a class, with the exception that structures also work in regular C and not just in C++. 2, every member in a struct is by default public. And 3, in C, not C++, in C a structure cannot contain methods. Okay, so those are the restrictions of a structure. So in this case, I'm defining a structure that I just call struct X, which is more or less a placeholder. Type 1 is a placeholder for the type of member M1. Type 2 is a placeholder for type M2, for member M2, and so on. So there are n members in this particular example. The text here talks about alignment, okay, and go through some really kind of awful looking math here to do the calculation of the offset to a particular member. If we are running out of time, okay, all of these considerations are not important for in the context of TTP ASM, but in the context of a 64-bit or 32-bit architecture, which you are more likely to be using in the future, these are important, okay? But I'm going to skip over those for now and start with TTP implementation. So in TTP implementation, if this is the definition of a structure, okay, I'm missing a semicolon here, but the idea is still the same. The first question now is, can we really do this? Can we refer to struct X when struct X is being defined on this line? What do you think? For those of you who have taken CISP 430, I really doubt how many people here have taken 430. You go like, yeah, I have seen this kind of definition before. But if you have not, how many bytes should I reserve for PTR, for pointer? And we'll just assume that we are doing everything in TTP ASM. So how big is a pointer in TTP ASM? I'll give you two options to choose from. One, it kind of depends on how big a struct X is. Two, it is 1 byte. So what is the size of pointer? It is just 1 byte, okay? Every pointer, regardless of the type of things that it points to, is just 1 byte. Why is that? Well, that's because the A port of the RAM that we use in TTP is only 8-bit wide. So that's why all addresses can only be 8-bit wide. It does not matter what it points to, okay? The address has nothing, the size of the address has nothing to do with what it points to. It has to do with the size of the memory itself. So in our case, we have an 8-bit address port with our RAM, so every address is only 1 byte. All right, so the translation is this. So in assembly code, we are basically saying the first element is at an offset of 0 from the beginning of the structure itself. And then the second item is right next to it. So we look at the offset to the first item and add to it the size of the first item. And then the last item, the third item, is the second item, the offset to the second item, plus the size of the second item. So this one is basically saying all pointers are 1 byte wide. And then we also have to define the size of the entire structure, which is the offset to the last thing. Okay, I got this wrong. This is supposed to be x underscore y 1 plus, because it refers to the offset to the last member plus the size of the last member. So let me go ahead and fix that first, okay, because I hate to see something wrong and just kind of leave it wrong like that. So I'm just going to look for that. It is x underscore size. And there we go. Okay, so I'm going to fix this. Might as well fix the other one too. Put a semicolon here. And after this is fixed, it takes about a minute to refresh the content. So I'm just looking at the clock here, looking at the second hand. All right. So, okay, so as this is getting updated, the next question is, can we see this in C code? The answer is, yeah, we can actually see this in C code. So I'm gonna go to online GDB, and I don't even have to sign in. All I have to do is to specify I'm using C code and control. Okay, I'll just go ahead and erase a whole bunch of stuff like this. Get rid of all that. Pound include stdint.h struct x. Oops. And you have to remember to put a semicolon after a structure definition. That is not needed when you have a class definition. So here we have u8 underscore t x. Okay, we'll just go ahead and say xyz. Okay, I cannot do pointers here because pointers in a 64-bit architecture is 64-bit wide, And that introduces some complications that I don't want to talk about right now. So right here, we can change this to a Z. And then in main, I'm going to say, okay, we have a struct x, and I call that var, okay, as a variable. And we just want to say one thing, var dot x equals to 0, just so that it doesn't optimize the local variable out entirely, because otherwise the compiler does optimize things that are not getting used. So I'm going to put a breakpoint here, and then we'll go ahead and debug this code. So run the code, we're now up to here. So the question now is, I go to the command line, and I ask, where is local variable var? I should say ampersand var. Okay, it's hard for you to see, but it ends with EB3D, okay? So the last two digits, the least significant two digits is 3D, okay? So go like, okay, what about the address of the first member, which is called X? It is the same. It's hard, it's really kind of faint for you guys to see it. I wish I know how to turn off syntax highlighting in GDB. Well, let me see if I can do that. Turn off syntax highlighting in GDB. Set style enabled off. Okay. Set style enabled off. Let's give it a try. Set style enabled off. Cool. Let's do it one more time. Haha, that works. So you can see the address of the structure of the member is 3D, but the address of the entire structure is also 3D. All right, so does everybody understand what we are looking at right now? Okay, the conclusion is the address of the first member of a structure is really the same as the structure itself, the address of the structure itself. That kind of makes sense, right? Because if a structure has to contain several members, kind of makes sense not to waste any space at the very beginning and just say, hey, the first member of the entire structure, why don't you live over here? Is that okay? Okay. So it kind of makes sense that the next one is right after that. Okay, so now we want to print, where do I find the second member in this case, which is member Y, in memory? You can see that, oh, it's right next to it. What about the third one, the Z? It's right next to it too. And then if you ask, how big is a struct X? What do you think? Three bytes. Yep, that's exactly what it is. So I'm only replicating what we are observing in GDB in assembly code. Okay, so in assembly code, I cannot define the structure, but I can use label definitions so that I can understand how a structure is laid out in terms of memory. Okay. So I think it is updated by now. We can go back here and just kind of go back to the previous slide and have it update itself. So this is updated, okay, it is correct, and this is also updated. Is that okay so far? So this, yeah, go ahead.
What happen if X is a constant, like a 57 or something like that? How many bytes would that be?
Say that one more time.
What happen if when you define the structure, you define X as a constant variable, saying that X is always going to be 57, for example? How many bytes will that calculate to?
I believe it would not make any difference. Okay, so let's give it a try, okay? So when you say const, okay, what you're really,
Yes.
I'm not even sure that you can do it to a struct, but we'll give it a try. Because I'm not even sure this is doable in a, in C, in a struct, but we can give it a try. Okay, so we say const this one equals to 14, okay? So I'm not even sure whether this compiles or not. Okay, so let's just say that it does. It does not compile. Yeah. Because in C, in regular C, you cannot designate a member in a structure to be a const. Const for the most part, okay, not all the time, but for the most part, it is really just a rule for the compiler to self-check. so that if you try to change anything that is a const, the compiler goes like, you're not supposed to touch that. Okay, so let me illustrate what I mean by that. Okay. You cannot even do initialization in the struct definition, because that's just not one of those things that you can do. So a struct definition in C, not C++, is a very simple thing. All you're doing is to say, okay, we are bundling these things together, and so that we can refer to this entire thing if we want to as one thing, or we can break it up into the individual members and refer to the individual members. That's the whole point of a struct. It does lead to classes, okay? Because a struct is the predecessor of a class, along with all the other object-oriented programming concepts, that goes along with classes. But a struct is basically just a way to package things and say, okay, these things collectively can be seen as one thing. All right, so let's go ahead and use a const over here. So const and we'll say xyz equals to 5, and then later on we say let's go ahead and change it. XYZ equals to 10. Okay, so the compiler would actually complain in this case, because the whole point of this is for the compiler to complain. The compiler says, hey, this is supposed to be a constant. The question is, can I override it? Can I tell the compiler and say, it's okay to do this, trust me, I know what I'm doing? Okay. The answer is, I think it can be done, okay? Because what you can do is to cast xyz into just a regular integer without the const, okay? So we'll go ahead and give it a try, okay? It says L value required as a left operand of assignment, okay? L value required. So xyz does not have an L value in this sense. Okay. All right. So that got me a little curious. Okay, so we'll go ahead and debug this program, got rid of that line, and then just run the code. Okay. Because what I want to do is to say, where is var? Okay, var is, I need to set style enabled off, right? So now I want to print where is var, print where is var, and I want to say where is xyz. So xyz does have a place, and it's a local variable, but it won't let me change the location. All right. So one thing that I'm interested in all the time is how to circumvent around things. So now I say, okay, if xyz cannot be casted to a regular int, how about this? The address of xyz casted into an int pointer first, and then dereference it, and then put this over here, which is my way of circumventing that xyz is supposed to be a constant. So we'll see whether this compiles or not. It does compile. Cool. So now we continue, run the program on the hello world line. Okay, not useful at all. Now we are on the return 0. All right, so I'll let you guys place your bets. Do you think xyz is still a 5 because it's supposed to be a const? Or do you think my assignment operation on line 17 was successful so that xyz is actually a 10 at this point?
Didn't you kind of force them to change it?
Yeah, well, casting the address of something into something else is how you can get around some restrictions and lead to all kinds of other problems at the same time. This is something that you can do only in C and C++, okay? Casting a pointer to something, to anything you want to, really, okay? And say, yeah.
This is why one of the vulnerabilities of C in terms of like security.
Yeah. Yep. Well, okay, so from the security perspective, it mostly has to do with any pointer can be seen as an array. Okay, any pointer in C can be seen as an array, so you can start indexing. But is it really an array, and do we know the size of that array? The answer is no. Okay, In most scripting languages, I think you're familiar with Python and JavaScript, okay? You can actually ask an array and ask, what is your length? And the array is aware of its own length. So when you try to index out of that length, either it will give you an error, like, oh, you're trying to index out of range, or it will make the array large enough for that, right? But in C and C++, there's no such thing, because an array is nothing more than really just a pointer to the very beginning of the entire array. The C compiler does not know how long the array really is. The runtime code also does not know how long the array is. So if you want to index out of the range of the array, you can actually do that. But then you'll be walking into other things that are next to the item that you're trying to access, but not really that item itself. It's bad enough if you're trying to read from those locations, because hey, what business do you have to read into those locations? But it's worse when you're writing into those locations, because then you can overwrite really kind of funky stuff, on the stack. You can overwrite, for instance, the return address. So what happens when you overwrite the return address? When the function returns, it'll return to the wrong place. Now, it's one thing to overwrite the return address, so it's not even valid anymore. It just returns to La La Land. If that is the case, count yourself lucky, because that means the program just crashes right away, okay? You can overwrite the return address. Okay, tell me again. In a 64-bit architecture, like the AMD 64 instruction set, how long is an address?
64.
64-bit long, okay? So if you say I'm accessing, things as an array, and you're only changing 8-bit or 1 byte at a time, you can change the least significant byte of the return address so that the resulting address is still valid. It is still some place that you can return to, even though you're not supposed to return to. So in that case, your program, when the function is all done, it will still return. It will still return to close to where it is supposed to go to, except it's not exactly where it's supposed to go to. So you can call function f, and then the return point is someplace right before the call to function f. So in that case, it's very hard to debug those programs, because when you try to single step through the program, you go like, it doesn't make sense. Okay, when function f returns, it's supposed to return to right after the function call itself, but instead it returns to some place that you don't expect it to return to. So whenever you see something like that, when you're debugging a C++ or a regular C program, think about stack corruption. Okay, because the stack corruption can give you symptoms that is impossible to explain without knowing what we learned in this class. How the stack is being used, how the return address is on the stack. But when you work with AMD 64, which is a far more complicated platform, it's not just the return address that is also stored on the stack. There's also the frame pointer and a few other things. When those things get corrupted, it will give you symptoms like this. It is entirely possible to write a program where the function itself is fine, but when the function returns to the caller, every variable is like 4 bytes off or 8 bytes off or something like that. So variable x becomes variable y, variable y becomes variable z. It's like you have no idea how that can possibly happen. When something like that's happened, suspect stack corruption. Because the symptoms of the stack getting corrupted because you're accessing an array out of bound, there's no fixed symptom. I cannot just say, oh, if these things happen, it is because of the stack corruption problem. It can range, there's a wide range of how the symptoms may seem to you. So, anyway. Any questions before we kind of stop the recorder for today's lecture? No other questions? All right. So if there are no other questions, I'm going to stop the recording. And during the lab time, if you want me to help you get River Spider installed, go ahead and let me know, because I can certainly do that. If you're using a PC, both the PC here and the PC at home running Windows, I highly recommend that you put SIG-Win or SIG Reaper Spider onto a thumb drive so that you can carry that environment with you, whether you're here or home, that your memory stick will still work. So that's just my recommendation. All right, so I'm going to stop the recorder because I don't see any people asking any questions.